Welcome to the third video on the chapter of measures and location of spread for chapter 2. So this is going to talk through finding means, medians, modes and range again, and also looking at the problem of interpolating data using a different method which you may well prefer. And possibly most importantly, we're going to take a look at what's called standard deviation. So I'll show you how to find this first of all today without using a calculator, but then later on I'll show you how you can use your ClassWiz to find these statistics very easily indeed. So first of all, as usual, if we could have a look at some warm-up questions. Here they are this time. 1, 2, 3, 4 as usual. So press pause now to have a go at them yourself, and once you're ready, press play and we'll go through these answers together. Okay, so let's have a look now at question 1. So question 1, we're asked to calculate Q1, Q2 and Q3 for the following data. So at this point it's worth recapping what we mean by Q1, Q2 and Q3. Well, Q1 just means the lower quartile. Okay. Q2 is another way of writing the median. It's the second quarter, 2 quarters is a half, that's how you can think of it as being the median, and Q3 is the upper quartile. That's what Q1, Q2 and Q3 will always mean. So I'll show you how to do this manually, I'll then show you how to do this using the ClassWiz. So the easiest one to work out, I would say, would be the median. So we can work in from the middle, so it's never going to be the end values, so not this one or that one, nor this one, nor that, nor this one, nor that one. So the median, the middle one, is going to be 5. So we can write that in straight away. So the median is 5. So what we can do now is we can work out the lower quartile and the upper quartile when we're talking about discrete data, definite countable data, not continuous. We can think of this as being relative to the median. And so once we have the median, we can sort of forget about this now and consider the left-hand side as one wing and the right-hand side as the other wing. We now look for the medians of each side, having scrubbed out the median. So the median on the left wing will be the lower quartile, the median of the right values will be the upper quartile. So the lower quartile, find the median of these numbers. Again, as ever, the median isn't going to be the end ones, it's the one in the middle. So for this one, the lower quartile is going to be 2. And in the same way, the upper quartile, looking at these higher numbers, these are the 2 end ones, 8 and 15. The middle of these numbers to the right-hand side is 11. So for that reason, the upper quartile would be 11. Now in the exam we can do this using a calculator very easily indeed. So if you get your ClassWiz up and ready, here it is. What we can do next is press menu and scroll along until we get to statistics mode, number 6, and press equals. Now we want one variable. There's only one variable here in this data set. So press 1 for one variable calculation. And now we can just put the numbers in one by one. So x just means the particular value we're inputting. So the first one is 2. Press again because we have 2 2's. Press 3. The next one here was a 5. You can just about see it. Then 8. 11. Whoops, not 111. And then finally 15. We now press AC, but don't worry, it's not going to erase all the data. So press AC, then press OPTN, so we can get options for these data. So press OPTN. We want to press 2, one variable calculations. So the calculator will now perform calculations based on the data we've just entered. So press 2. So here we have all this summary data. So what I'm going to do here, I'm going to try and enlarge this for you so you can see it more clearly. Okay, so this is what we've got on the calculator display. So this means the mean, x bar. This looking looks like an E. X, that means sigma x, that's the sum of all the values. This is the sum of the values squared. We'll come to this later today, by the way. But if we press down on the calculator, you can see Q1, median, which is Q2, and Q3, 2, 11, and 5. And so if we compare these to what we had doing it manually, 2, 5, and of course 11. So it does compute exactly as the calculator would have worked it out. So let's have a look at worked example 2. For number 2, again we've got to calculate quartiles. So calculate the lower quartile, upper quartile, and the interquartile range for this following data set. Again, I'll show you how to do it manually, but at this point I can't stress enough how much easier it is to use the calculator. So I'm just going to show you it manually, just so you can see that the calculator is generating sense. It's not just coming from nowhere. So, like before, the best thing here is to calculate the mean and then eliminate the mean from the data. So, first of all, we know that the mean is not going to be at the ends. So working in from end to end, it's not going to be these end three, that one, or that one. So now we're left with two numbers in the middle. So now the median must be halfway between 18 and 19. So what we do here is we need to add in the median, because the median doesn't exist in this data set. So the median is 18.5. Now we've added it in, we scribble it out. And then think about the left-hand side and the right-hand side. But we didn't scrub out 18 and 19. And so 18 and 19 are still included in the left wing and the right wing, as it were. So now what we need to do is to find the median of these 5 numbers on the left-hand side. So it's not going to be the end ones. It won't be 4 or 18, 5 or 11. So the median on the left is 9, therefore the lower quartile is 9. We do the same on the right-hand side. So the median won't be the end ones. It won't be 19 or 29, nor 20, nor 24. So the median of the right-hand side numbers, which is going to be the upper quartile, is 21. So then Q3 is going to be 21. From these two values, we can then work out the interquartile range. So therefore, the interquartile range, IQR, is going to be 21 subtract 9, which is 12. But again, always best doing these on the calculator. So press menu again. And then when we press menu, we're after going for option 6. So 6 statistics. So press 6 or equals when you're on 6. And again, we want the one variable calculation option. So press 1, and then we input the data values one by one. So first of all, press 4, because 4 is the first value, then equals, then 5, so press 5, equals, 9, equals, and so on. 11, 18, 19, 20, 21, 24, and 29. Press equals for the last number, then press AC to clear this off from the calculator screen. It's not been lost from memory, it is still stored. So to perform calculations on what we just entered, press OPTN for option, then press 2 for one variable calculation. And again, I'll make this bigger for you so you can see it clearly. Here's the data been calculated, all these statistics. So this page isn't of interest to us for this particular question. So scroll down, press this button here on your calculator. And we want here Q1, which is 9, which is what we got, and Q3, which is 21, 2. So this calculator doesn't tell you the interquartile range, it doesn't quite do that much for you. But obviously, once you've got Q3 and Q1, I'd like to imagine you can do this next step yourself by doing 21 minus 9, which should give you 12, which is indeed what we got via doing it manually. So that's all there is for question 2. Question 3. We're told a garage keeps records of the costs of repairs to its customers' cars. The table below gives information about the costs of all repairs which were less than £250 in 1 week. So for question 3, we need to calculate the class interval in which the median lies. So the best thing to do here, I would suggest, would be to do a running total. In other words, cumulative frequency. So the first frequency is 4, so just write 4. What we're going to do is we're going to keep adding these frequencies until they eventually grow to give a total frequency for the whole table. But we're going to stop as soon as we get to more than halfway. The median is going to be halfway within the data set. And so what we need to do here is to actually think about what the total of all these will be. Then we'll refer back to the cumulative frequency. Carrying on with the cumulative frequency, 4 plus 8 would give us 12. 12 plus 7 is 19. 19 plus 10 is 29. And finally 29 plus 11, that gives us 40. So the median is going to be, because this is continuous data, we can just take the total frequency and divide by 2. So the median here will be the 20th value. So now this is where the cumulative frequency comes into play. We look for the first cumulative frequency entry which exceeds the median value, the position of the median, I say. So we're after the first value here, which is above 20. And the first number which goes above 20 is this 29. So another way of thinking about it is the first 19 data points are in these first 3 intervals, but then the 20th, 21st, 22nd and so on lie in these last 2. So the median has to be in this interval here. In fact, it's the first one in this class interval. The 19th is in this one, and the 20th is in this one of 150 to 200. So the median is in this interval. So we just write 150, C, 200. And that's the class interval that the median must be inside. Lastly, question 4, and this is where we're going to return to the previous lesson, calculating percentiles for continuous data. So again, I'm just going to adapt the cumulative frequency from last time. This time I'm going to start from 0, 4, 4 plus 8 is 12, 12 plus 7 is 19, 19 plus 10, 29, 29 plus 11 is 40. Now the 80th percentile, we need to think what position the 80th percentile would be. So 80th percentile, percent means 80 out of 100. The total frequency is 40. So the 80th percentile will be the value which is 80% of 40. So let's work this out. You could do this without a calculator, but if you have one, you may as well just treat yourself and use it, I suppose. So press menu, then 1 to get back into normal mode, if you're outside of normal mode. So 80% of 40, that gives us 32. So the 80th percentile means we want the 32nd value. So whereabouts would the 32nd value be? Well, let's have a look at these cumulative frequencies. So we can see here that the 32nd value would have to be between 29 and 40. So the 32nd value would be here somewhere. Okay, we then need to think about whereabouts that would be within this interval. And so let's now add in the interval boundaries for all of these intervals. So the first one is 0, then we have 50, then 100, then we have 150, 200, and 250. So now we think of this in terms of relative fractions. And so think about where 32 is within this class interval from 200 to 250. So 32, take 29, work that out as a fraction of the full class width. So the full class width, so the full frequency is from 40 to 29. So that proportion must be the same as the proportion of the 80th percentile within this cost between 200 and 250. So I'm just going to add in P subscript 80 for the 80th percentile. And so how far P80 is within this interval from where it starts at 200, it's going to be P80 minus 200, and that as a fraction of total class width is going to be that as a fraction of 250 minus 200. So let's simplify this. 32 take 29 is 3, 40 take 29 is 11. The top gives us P80 minus 200, and at the bottom 250 minus 200 is 50. So we can now rearrange this to find the 80th percentile. The 80th percentile, which is P80, is this 3/11 multiplied by 50 and plus this 200. So if we work this out now, so type in 3 over 11 multiply by 50 plus 200. Now we may as well give this to, we could give it to the nearest pound, which would be 3 significant figures, that's fine, or we could give it to the nearest penny. It really doesn't matter, it's an estimate anyhow. So what I'm going to suggest here, we can give it to the nearest penny, why not in this case? If in doubt, give answers to 3 significant figures. But here, let's just do this to the nearest penny. So £213 and 64 pence is what it would be. 213.64. And that concludes the warm-up. But by the way, if you're not liking this method for finding percentiles or data points using interpolation, the next part of this lesson will show you an alternate method which gives you the exact same answers but using a way which I personally find easier. So the main Edexcel textbook uses this way. I've got an alternative which I personally prefer. I'm not saying one is necessarily better than the other, but I do have an alternative way to doing this. And so if you're not a fan of this, fear not, I will give you another method now. So let's reveal this new method. So the new method for interpolation with continuous class intervals. This method, for the record, is my preferred way of doing it, but I'll show you this method. You can compare it to the one shown in the previous chapter, and then you can draw your own conclusions about which you prefer. So either this method I'm going to show you or the previous one are absolutely fine, just pick your favourite. So this way. This method is different to the method explored so far for dealing with interpolation with continuous class intervals. So it can be considered differently here, which is what I'm going to show you, but we still get the exact same results using this method I'm going to show you now. We still need to calculate in which class interval our statistic's located, and from that we can then work out the relative position of our statistic within that class interval. Finally, we estimate how far within the interval it lies as being directly proportional to its position in that interval relative to other elements in the interval. So the assumption we're making here is that within any interval, the elements in that interval are evenly spread out. That's the assumption we're making when we interpolate. The estimated value of our statistic, call it V, so V might be a quartile, a percentile, a median, is given by this formula here, which is nowhere near as bad as it looks. All this is essentially is something that boils down to working out fractions of amounts. So I'll explain what these terms here mean now. So the lower bound subscript Ci just stands for the lower bound of the class interval containing our statistic in question. Position Ci just stands for position within that class interval. So it's the position of the statistic in question within that class interval. So is it the first in the interval, the second? Is it the third one inside the interval? And so on. Frequency subscript Ci just stands for the frequency of that class interval which the statistic is in. And width Ci is the class width of that class interval. So looks a bit intimidating, but I can promise you this method is quite simple, and I'll illustrate it now in the next example. So worked example 1. I'll show you 2. So the first one, we've got a newspaper which has asked its readers how much time they spend playing video games each week. The table below shows the responses in minutes. Calculate estimates for A, the median, and B, the 90th percentile. So what we're going to do here, first of all, is we're going to do a cumulative frequency along the top for the times, and then a literal cumulative frequency on the bottom for the frequencies. So first of all, the time, the lower interval here, lower boundary is 0. So sorry, I mean along the top we're going to do the boundaries. Between 20 and 20, that boundary is 20. Now this raises an important point. If we had continuous data where the class intervals didn't run into each other, for example, if this said 19 and that said 20, we'd put 19.5 here. So we always go halfway from the upper of one and the lower of the other, if they don't overlap. Here though, they do touch, so we just put 20. Between 60 and 60, this boundary is 60. This boundary here is 120, and so on. We go all the way to the end at 1000. At the bottom, we do the cumulative frequencies. So we'll start from 0, still 0. 0 plus 15 is 15. 15 plus 18, that's going to give us 33. 33 add 25 is 68. And 79. And finally, 79 plus 11 at the very end gives us 90. 79 plus 11 isn't 80. So thank you very much, Erin. 79 plus 11 is 90. So now what we need to do for part A is calculate an estimate for the median. So what we need to do now is first of all think about what position the median would be in. Well, we've got 90 values, and so what we need to think about now is what position of the 90th the median would be in. Well, if there's 90 values, the median will be halfway along, and because it's continuous data, we don't need to think about adding one on or anything like that. So it's just going to simply be 90 divided by 2, which is 45. So that implies that the median is the 45th value. So because it's 45th value, we can now think about using these cumulative frequencies, whereabouts the 45th value would be. So the 45th value is clearly going to be in between the 33rd and the 68th. So the median, which is 45th one, will be somewhere here. So I'm going to call this the median. And so the median is therefore going to be in this class interval from 120 to 300. So we can just add this in now. So from 120 to t to 300. Now for this class, the lower bound just means where this class starts. So the lower bound for this one is 120. The position of the median in this class, well, the median is the 45th value. So how far in after 33 is the 45th? Well, it's going to be 45 minus 33, which is going to be the 12th one. So we can say it's going to be 45 minus this 33. So it's going to be the 12th one. Put into brackets where we get the 12th one from. So it's a 12th value in the interval. The frequency of this class interval, as you can see here, is 25. And the width of that class interval, it goes from 120 to 300. So the width is 300 minus 120, which is 180. Now we've got all the ingredients we need to calculate the estimated value of the median. So we start where the interval starts. So we're going to start at 120. We're now going to add on 12, because it's a 12th value. That's a 12th value out of a total of 25. So we're going to add on 12 25ths of the width of that whole interval. So the median is almost halfway in. 12 25ths is about halfway. So we're after this fraction of 180 within that interval. So we're starting at the beginning of the interval, and we're going to go a fraction of the interval into it. So this fraction of 180. And that will give us the position, estimated value, of the median. So if we just calculate this on the class whiz, so we're going to do 120 plus 12 25ths of 180, and that gives us 206.4. So the median, our estimated median anyway, is 206.4 minutes. Next up, we need to calculate the 90th percentile. So the 90th percentile is going to be where the 90th percent of 90 is. So we need to work out 90% of 90. So 90% of 90 that's going to be equal to 81. So therefore, the 90th percentile, P90, is going to be the 81st value. So now we need to think about the class interval containing the 90th percentile. Well, 81 is between 79 and 90. So we know that the 90th percentile must be in this interval here, between 79 and 90. So now what we need to do is just list that it's in this interval from 600 to 1000. Next, we're going to write the lower bound of that class interval. So this class interval begins at 600, as we can see. And the 81st value, the 90th percentile, if this one starts at after the 79th, then 81 take away 79 is going to be the second one in this interval. So it's going to be the second value in the interval. And I'll mention where we get the second from by putting it in brackets if ever you're not sure where we're getting it from. So it's going to be the position of P90 which is v80 first. So we write down 81, and we subtract from that where the interval begins. It begins after the 79th. So 81 minus 79, that obviously equals 2. So that's where we get the second value from. It's the second out of 11. So we write down 11 here, because that's the frequency of that class interval. The width of that class interval, it goes from 600 up to 1000. So the complete width is 1000 minus 600, which is 400. We can now calculate the value, the estimated value of the 90th percentile. So we start where the interval starts, so we're going to start with 600, and we're going to add on, because this one's the second out of 11 in this class, we're going to add on 2 elevenths of 400. So 2 elevenths of 400. So we just type this into the trustable ClassWiz and see what pops out. So 600 plus 2 elevenths of 400. We get to one decimal place, 672.7. So we get 672.7 minutes. And from part A we had that, so that's the first worked example all done. Let's have a look at worked example 2. So we've got this table that shows the masses in tons of 120 African bush elephants. So as you can expect, they're going to be pretty large indeed. And we need to find 3 different things: estimates for the range, the interquartile range, and the 10th to 90th interpercentile range. So the range, which we need to estimate, is quite a strange one. We can't estimate it, but we need to take the absolute upper limit of the range. So obviously the range is the highest to take the lowest, which you should probably remember from GCSE. But the highest here could be anywhere from 6 to 6.5. So do we take the midpoint or anything higher? Well, what we do is we take the absolute extreme value. We take the absolute upper bound of the greatest interval. So we take 6.5 as our maximum possible highest, and equally we subtract the absolute possible lowest, which is 4.0. And so the range estimate, which is going to be an upper bound of the possible true ranges, is the upper limit 6.5 minus the lower limit of 4.0. So our range is going to be 2.5 tons for part A. So obviously we're not saying the exact range is necessarily 2.5, but this is just our estimate. For part B, we need to find the position of Q1. So Q1 is the lower quartile. So as you'll probably know, the lower quartile is 1/4 into the data. We're told there's 120 African bush elephants, so the lower quartile, we do that by working out 1/4 of 120, which is 30. Therefore, the lower quartile will be the 30th value. The class interval containing Q1, well, if we just label Q1, which is the 30th, whereabouts is the 30th value? Well, the 30th value needs to be probably somewhere here, but this is where we need to do the class interval limits at the top and the cumulative frequency at the bottom. So let's do this. So this lower limit is 4.0. This boundary between 4.5 and 4.5 is 4.5 itself. Like I said before, if you encounter a situation where these limits aren't continuous, where we don't flow one into the other, you'd take halfway between them as this limit. So for example, if this were for 4.0 and this were 4.5, this number here would be 4.25, halfway between them. That's what you do if these limits, this upper and that lower, don't run into each other. Here they do, so we don't need to worry about that. The next one, this limit here is 5.0. You could say just 5, I suppose. This one's 5.5. Up here is 6.0. And the absolute upper is 6.5. Running total of frequencies, for cumulative frequencies, we start at 0. 0 add 13 is 13. 13 add 23. That gives us 36. 36 add 31. That's going to give us 67. 67 add 34. That gives us 101. And finally, 101 plus 19. We end at 120, which makes sense because 120 is the total of all these elephants. So now, the class interval containing Q1. Q1's a 30th value, which is somewhere here. So because it's in this one, we know that the interval which contains Q1 has to be this one from 4.5 to 5. So we can just add this in as a little mental note. The lower bound of this class interval is at 4.5. Now, what position is Q1 in this interval? Well, this one is the 30th along, but the interval starts at 13. So we do 30 minus 13, which is 17. So that tells us that the position of Q1, the lower quartile within this interval, is a 17th value within this interval. The frequency of this interval is 23. And so therefore, Q1 is 17 out of 23 values in this interval. The width of this interval, if you notice actually, all these intervals have a width of 0.5. From 5 to 4.5 is 0.5, and they all have that same width. We can now work out the value of Q1, an estimate for it at least. So we start at the lower bound of the class, 4.5. Then because Q1 is a 17th value out of 23, we add 17 23rds of the class width onto that. In time, I'm hoping you'll start to see this formula is actually quite intuitive. 4.5 plus this fraction of the width. So let's work this out now. So 4.5 plus 17 over 23 multiplied by 0.5. To 3 sig figs, we get 4.87 tons. We can now apply the same idea for Q3. So the position of Q3. Well, Q3, the upper quartile, is 3/4 of the way along the data set. So we work out 3/4 of 120, which is 90. So the upper quartile must be the 90th value. The class interval containing Q3, well, let's just add in where Q3 is. So the 90th value is between the 67th and 101st, obviously. So we're looking somewhere here, where the 90th will be. So the 90th value must be between 5.5 and 6. So we can add this for what our class interval is that contains Q3. It's the interval that goes from 5.5 to 6. The lower bound of this interval is 5.5. The position of the upper quartile within this group, well, this group starts at 67, the upper quartile is 90. So to work out how far into this interval it is, we do 90 subtract 67. And if we do that, use a calculator, it'd be my recommendation, we get 23. So it's a 23rd value out of the 34 in that class interval. The width of this class interval again is 0.5. So now we can compute the value of Q3. So Q3 We start at the lower limit of this class interval, which is 5.5. Then because Q3 is a 23rd value out of 34, we add in 23/34ths of the width of that interval. So 23/34ths multiplied by 0.5. Let's just calculate this on the class whiz. So 5.5 is what we start with. So type this in. Plus fraction button, 23/34 multiplied by 0.5. Press equals SROD. We get for that one 5.84 tons to 3 sig figs. We can now do the interquartile range. So the interquartile range is going to be the upper quartile, Q3, subtract the lower quartile, which is Q1. So the interquartile range is 5.84 Q3 minus Q1, which is 4.87. So if we do that on our calculator, so 5.84 subtract 4.87, we should see that we have 0.97 tons. So from the elephant which is the lowest quarter to the elephant which is 3/4 long in terms of how much it weighs, how much the mass of it, it's about a ton difference between those elephants. Let's now have a look at part C. For part C, we're talking about percentiles, in this particular case, we're talking about the 10th and the 90th percentile, and then the 10th to 90th interpercentile range. So the first thing we need to do for this one is to calculate the position of P10. Well, P10 stands for 10th percentile, so it's going to be 10% of the way along these elephants. So we work out 10% of the total elephants, which is 120, and 10% of 120 is 12. So we're wanting the 12th value. So the 12th value is somewhere between 0 and 13, so it might be about here, let's say. And because of that, we can see already that the class interval containing P10 must be this one here, from 4 to 4.5. So we can label this in our notes. So from 4.5 is the class interval containing P10. The lower bound of this class interval, it begins at 4, so we put 4 or 4.0 if you prefer. The position of this statistic within this class interval is the 12th one, as you can see, out of the class frequency of 13. So it's a 12th out of 13. And again, like all these class widths, this class width is 0.5. We've now got all the ingredients to calculate an estimate for P10. So P10 will be the start of this interval, so 4.0 or 4, depending on how you think about it. Now, P10 is 12 out of 13 values in this interval. So we do 12 out of 13, 12/13ths of that class width. So 12 over 13 multiplied by 0.5 and calculate what that's going to give us. So we get this calculator up. So 4 plus 12 over 13 multiplied by 0.5. That equals to 3 sig figs, 4.46. So P10 is 4.46 tons to 3 significant figures. Then position of P90. Well, P90 is the 90th percentile, so we need to calculate 90% this time of 120. So 90% of 120, try this on your calculator if you'd like, you should find that it's the 108th value. So just as P10 was a 12th value, we need to work out now whereabouts P90 would be. It's 108th, so it's going to be between 101 and 120. It's going to be here somewhere. So 108th one is somewhere here. So as we can see, it must therefore be in the class interval from 6.0 to 6.5. The lower bound of this class interval is at 6, or 6.0 if you'd prefer, and the position of 108th value, the position of P90 within this class interval, is going to be 108 minus 101, which is where this class interval begins after. It begins after 101. So 108 minus 101 gives us 7. In other words, the 90th percentile is the 7th value within this class interval. The frequency of this class, we can see it's 19, and the class width, as all of them, the class width is 0.5. So we now have all the ingredients to calculate the 90th percentile, and therefore the 10th to 90th interpercentile range. So P90, we start at the lower boundary of this class interval, so start at 6.0. Then we're going to add in 7 over 19, because it's the 7th one in out of the 19 values in this interval. So 7/19 of the width of that interval. So we work this one out. So 6.0, or just 6, plus 7/19 multiplied by 0.5. That gives us, to three significant figures, a value of 6.18 tons. We can now calculate the 10th to 90th interpercentile range. So that's going to be P90 minus P10. The higher percentile take away the lower percentile. So we had 6.18 for P90, subtract 4.46 for P10. So 6.18, subtract 4.46. You can do this again on the calculator we can trust more than anything. So 6.18, subtract 4.46. That gives us a value of 1.72 tons for the 10th to 90th interpercentile range. So you've now seen two ways of how we can calculate interpolation questions. Take your pick over which one you prefer. This method here is my particular favourite, but it's up to you. Pick whichever one you feel most comfortable with. Let's next have a look at some harder examples for interpolation. So far what we've done with interpolation is we've been finding estimates of values of statistics within a data set, so quartiles, percentiles or whatever. So what we've done here is we've known the position of a value and we've found its value. We can go the other way round. So we can work out the position of a value if we know its value, rather than just working out a value from a position. So we can go both ways round. But once we work out of a position, whether it be the 1st, 2nd or 27th within a data set, what we might be asked from that is to estimate how many values at either side of the value we've found. So although interpolation is a tool for estimation, we need to be as accurate as we can be and to carefully consider the meaning of our calculations. This is particularly important when we're working out the position of a data value. So when our answers for the positions are whole numbers, it makes things definitely easier. So if we work out a position and we get the answer 4, that'll mean the 4th value. That's easy to interpret. However, when we encounter decimals in some cases, For example, how would we interpret the answer 63.13? What on earth would the 63.13th value even mean? When we get stuff like this, more care and thought needs to be taken in terms of what the numbers our calculator's giving us mean in practical terms. Here's an example to illustrate the point we've just been making. So worked example 3, what we've got here is a table showing how long people waited to the nearest minute in a phone call queue before being connected to a customer service advisor. So this is people maybe waiting to speak about their mobile phone contract or something like this, who knows. So we've got these wait times, W in minutes, in bands, and then the frequencies as you've seen before. So part A asks us to use interpolation to estimate the 30% to 70% interpercentile range. So what we do here is we put bounds on the class boundaries, we write these on, and we also do cumulative frequency underneath the frequency row, like we've done before. So let's start off by doing that, just as we've done many times before now. So for wait times, the lower boundary here would have to be 0, between 2 and 3, because these have been given to the nearest minute, that would be 2.5. Between 4 and 5 is 4.5. 6 and 7, 6.5. 10 and 11 is 10.5. And to fall into this last category, the wait time must have been, at the most, 15.5. 15.5 is the absolute maximum limit. So now what we do is do the cumulative frequencies. Start from 0. 0 plus 7 is 7. 7 plus 34 is 41. 41 plus 14 is 55. 55 plus 11 is 66. And 66 plus 4 gives us 70. So now we're ready to work out the 30th percentage point. So we could work out the 30th percentile. So what we do here is we think about what 30% of 70 is. So you can use a calculator for this, of course. But what you'd find is that 30% of 70 is 21. So therefore, the 30th percentile is going to be the 21st value. So now we can think about whereabouts value 21 falls in this data set. So 21 is more than 0, it's more than 7, but it's less than 41. 21 is in between 7 and 41, so we know that P30 must be somewhere in this category here. So the 21st value is going to be somewhere here, and I can label this P30. P30 is the 21st value along. So now we can interpolate to get an estimate for what P30 is. And so this class interval begins at 2.5. So therefore, the estimate for P30 is we're going to start at 2.5, because that's where the class boundary begins. Now, the 21st value is going to be the 14th in this interval. It starts at 7, but with 21 in. So how far in is a 21st after the 7th? We do 21 minus 7, which gives us 14. So it'll be the 14th one out of 34. So we add on this fraction, 14 out of 34, of this class width. From 2.5 to 4.5 is a width of 2. So we work this one out for our estimate. So 2.5 plus 14 over 34 multiplied by 2, and that's going to give us three significant figures, 3.32 minutes. So the 30th percentile is 3.32 minutes. Next, we can use the same idea to work out the 70th percentile. So whereas before we worked out 30% of 70, what we need to do now is work out 70% of 70. So on your calculator, or otherwise, you should see that 70% of 70 is going to be 49. So in other words, the 70th percentile must be the 49th value. So now we need to think whereabouts the 49th would fall. Well, 49 is more than 41, but less than 55. So the 49th value must be in this interval here, and likewise I'll label this at the top. That's where P70 is. P70 is the 49th value. So we can now form an estimate for the 70th percentile. We start where the interval starts. The interval where the 70th percentile is in, from 5 to 6, this begins at 4.5. So we start with 4.5. We now see that the 49th value is the 8th one in. 49 minus 41 is 8. And there's 14 values in total in this interval. So P70 is going to be the 8th out of 14. So we add on this fraction of this class width. From 4.5 to 6.5 is a width of 2. So now we just calculate this. 4.5 plus 8 over 14 multiplied by 2. That gives us two three significant figures, 5.64. So we've got P70, we've got P30. We can now go ahead and calculate the 30th to 70th interpercentile range. So the 30% to 70% interpercentile range is very much like the interquartile range. The interquartile range is the upper quartile minus the lower quartile. Here we just do the bigger percentile, the 70th, minus the lower percentile, the 30th. So the 70th percentile we had was 5.64. So we do 5.64. And we're going to subtract from that what we worked out the 30th percentile was, which was 3.32 minutes. So we subtract away 3.32. So 5.64, subtract 3.32, and what we have there is a 30th to 70th interpercentile range of 2.32 minutes. So after quite a bit of work, that's part A done. Part B, we're asked to estimate how many values fall within this range. So how many values fall within the 30th percent to 70th percent range. So what we need to do now is just to think about this in terms of common sense. So the 30th interpercentile point starts at the 30th percentage. So it starts 30% into the data and 70% stops 70% of the way into the data. So from 30% to 70%, what range is that? So what we can do here is do 70% subtract 30%, and we get 40%. So the 30th percent to 70% interpercentile range is going to include 40% of all values. Okay, so how many values are there? Well, the grand total frequency is 70. So now we do 40% of 70. and we work out from that as 28 values. Now 28 is a whole number, so we don't need to think about this any further. Because it's a whole number, we can stop, we can be satisfied that that's a reasonable estimate. However, what if this was 28.2? What if it was 28.5? You can't have 28.2 values or 28.5 values. In those cases, would we round up? Would we round down? Would it be as simple as just 0.5 or more we round up? Well, it wouldn't. So when we've got something a bit more complicated, which is what I'm going to show you for part D, there's a better way of thinking of this more carefully and more in depth than just thinking, well, if it's 0.5 or more, just round up. That might be okay for the examiner, because luckily this is still an estimate question, because we're using interpolation as an estimate, but there's an easier, more logical way of thinking about it than just either rounding up when it's 0.5 or more or not. So part D will answer your question, what if this wasn't a whole number? Anyway, for part B it's as simple as that, luckily, just 28 values, 40% of 70. Part C now. Calculate estimates of the mean and standard deviation for the dataset. Include units with your answer. And so the best thing I can suggest to do with this would be to simply use the class whiz. Okay, so for this one, let's just class whiz it up. Okay, so for the class whiz, what we need to do is include the midpoints. So using the class whiz, let's just add on the midpoints. From 0 to 2.5, that midpoint's 1.25. From 2.5 to 4.5, next midpoint's 3.5. Between 4.5 and 6.5, this next midpoint's going to be 5.5, so we need to fill this one in as well. Between 6.5 and 10.5, midpoint of that is going to be 8.5, and the last one, 10.5 plus 15.5 is 26, and half of 26 is 13. What we're now going to do is use the class whiz to generate an estimate of both the mean and the standard deviation. And so what we're going to do here is we press menu, and we press option 6. Once we've got option 6, we're given these different lists here. We press 1 for one variable. So now what we do, we need to make sure as well we've got this frequency column. As long as we've got the X, which we'll always have, we need a second column for frequency. If you don't have this, I'll quickly remind you how to get it. You press Shift, Menu, scroll down to Statistics, press 3, Frequency, press 1 to turn it on. So now what we do first of all is we type in the midpoints. So 1.25 is our first midpoint, then 3.5. Next we had 5.5. After that we had 8.5. And the last midpoint is 13. Now scroll back up and type in the corresponding frequencies. So the first frequency is 7, and 34, 14. I'll just see what the others were because I've forgotten. 11 and 4. So we type in 11, and the last one we type is 4. Once we have all these values, we then press the AC key, followed by OPTN in the top left, and option 2 to bring up the one variable calculations we've just put in. So as you can see here, we've got the mean. So the mean to three significant figures is 5.00 minutes. So we can type in that the mean, which we can say is W bar, is 5.00 minutes. And the standard deviation, again to three significant figures, we've got here is 2.85 minutes. So we're going to need this, what we've got from part C, to work out what to do in part D. So part D, it says to estimate how many values are greater than one standard deviation above the mean. So one standard deviation above the mean, what it's saying here is to add on one standard deviation to the mean. So one standard deviation is 2.85. Then add on that to the mean, so 2.85 plus 5, that's 7.85 minutes. And so we want to work out how many values are greater than 7.85 minutes. So what I'm going to do now, I'm just going to temporarily get rid of these midpoints we typed in to give myself more space. So now what we need to do is work out whereabouts 7.85 minutes would go. Well, it's quite clear that 7.85 minutes would be in this interval here from 7 to 10. So I'm just going to do an arrow here saying that 7.85 minutes would be about there. And then what we need here is an estimate for the position of the value, which is at 7.85 minutes. So I'm just going to put here P for position, subscript 7.85. So what position is that? Is that going to be the 57th value, the 59th? That's what we need to work out. So we can estimate this, again, using interpolation. Normally, the examples we've done so far for interpolation, we've gone from this scale to estimate the above scale, whereas now we're going to use this scale here to estimate the position on the lower scale. But we can still use the same exact ideas to do this. So what we're going to do first of all is to consider where this interval begins in terms of frequencies. This interval here, in terms of frequencies on the scale we want, begins at 55. So what we're going to say here is at the position of the 7.85th value, we're going to start where this interval starts in terms of position. So start at 55. We're now going to add on the fraction that 7.85 is within this interval. So 7.85 relative to 6.5 is 1.35 in from the start of the interval. And the interval width from 6.5 to 10.5 is 4. And so this here is a fraction within from the start of the interval that the position of 7.85 minutes should be. So 1.35 over 4 multiplied by the width of the interval. From 55 up to 66, that's a width in terms of positions of 11 values. 66 take 55 is 11. So we're going to do this calculation and see what we get. Just move this calculator to the side. So I want normal mode, so press menu option 1. So 55 plus 1.35 over 4 multiplied by 11. So that's about the 58.7 first value, which obviously makes very little sense indeed. Now this is why I want to talk you through this other method about thinking of this carefully. So 58.71. So what this is saying is 7.85 minutes that would have been, I'm going to put this in inverted commas as well because it doesn't actually exist. That would be the 58.7 first value. Now obviously you can't actually have in real life a 58.7 first value. It's either 58th or 59th. At this stage, rather than just simply rounding up or rounding down, I think it's best to think of it carefully in terms of how many are above 58.71, how many are below? I'll then mention at the end the dangers of just simply rounding up and rounding down, and why that might not work. So 58.7 first value is the critical point. So how many would be below 58.71? So in terms of actual whole number positions, first, second, third, and so on, below 58.71 there'd be 58 values. So we can write this down. So 58 values are below it. They're below 7.85 minutes. Then just remember how many values there are in total. Okay, there's 70 values in total. So 58 are below, then the other 12 must be above. So that's the final answer. So 12 values are above. 12 values are greater, if you like. So you may have noticed that at the end of part B, I was saying again and again about if it wasn't a whole number value, just as in part D, 58.71 isn't a whole number value. And I was going on and on. You might have been thinking, why is he so obsessed? I was going on and on about the dangers of just simply rounding up or rounding down. So let's imagine here we rounded up. So 58.71, that'd round up to 59. It would then be tempting to think, well, 59th value is where this one is, rounded up. So 70 take 59 means 11 would be above. But here you can see 11 isn't the same as 12. So thinking of it a bit more carefully, rather than just rounding up and down that much thought, would be the best way of doing it. So that's worked example 3 complete. So now what we now need to do is think about this new concept called standard deviation, which we're going to introduce to you carefully and also prove. So let's have a look now at this new bit, standard deviation. Let's introduce it then. So standard deviation, a little introduction for you. So we've seen the range. The range tells us the absolute difference between the least and greatest values in a set of data. And the interquartile range, on the other hand, tells us the difference between the lower quartile and the upper quartile, which is essentially how spread out the middle 50% of the data is. Unfortunately though, neither one of those statistics tells us how clearly or how dispersed the data is from the mean. So it doesn't tell us about the data relevant or relative to the mean. Is the data quite close to the mean, generally speaking, or is the data very spread out either side of the mean? So let's think now how we could find a way of measuring the average dispersion or spread. Fancy word for spread is deviation. How could we measure the average spread of data points from the mean? How could we measure how far away data points are on average from the mean itself? So let's just pick an easy data set. So let's consider the set of data of just 4 values, 1, 1, 2, and 4. So we could calculate the mean of this easily enough. So the mean, we add them together, 1 plus 1 plus 2 plus 4, which is 8, and divide by how many values we've just added up. So this is 4 values, so the mean would be 8 divided by 4, which would be 2. We could do the calculation like this. So the mean is 2. If we now consider a graph, I've put a graph in inverted commas here, because it's not quite a graph as such, but imagine an illustration of data points relative to the mean, like this perhaps. So the mean, I've done a line at 2, which represents the mean, and these 4 green dots represent the data points. So we've got 2 ones, which you can see are 1 away from the mean, 1 to the left, 2, which is bang on the mean, 2 was the mean itself, and 4 over here, which is 2 away from the mean on the right-hand side. Now, we can calculate the distance from the mean of each data point. To work out the distance, or difference of 2 things, we just do one, take away the other. But we need to keep the order the same. So let's do this by calculating the distance as the first data point, the data points subtract from the mean, rather than the other way around. And here we'd have it. So this one 1 take 2 would be minus 1. 1 take 2 would be minus 1 again. 2 take 2 for this one is 0. 2 is on the mean, so it's a distance of 0 away. It is the mean. And 4 take 2, that's 2 away. So we've got minus 1, 1 to the left, minus 1, 1 to the left of the mean again, 0, which means it's on the mean, and positive 2, which means 2 to the right. And so overall, how can we get a picture of these 4 data points combined? How far away they are in total? So we could sum these distances together. So sigma means sum, so we could add up all these differences which relate to the distance by adding them all together. So let's add these up and see what we get. So minus 1 plus minus 1 plus 0 plus 2. So you see here, we have them all together, we get 0. So that would seem to paint a picture that if we did the average of this, for example, 0 divided by 4, we get that the average distance away is 0, which is meaningless. And obviously we can see the average distance isn't 0 because some data points are clearly not on the mean at all. So this is possibly quite confusing. So how could we unconfuse a situation and build up something which is meaningful? Well, you might spot here that the problem's been because some of these data points are minus and some are positive. So the minuses have cancelled the positives. But of course, if you were calculating, how do you know whether to do one thing, take the other, or to switch the order of the calculation? It's going to be really awkward, isn't it? Especially if you're talking about lots and lots of values. So yeah, we have a problem because this isn't representative as a value for the spread of this data. The spread isn't going to be 0, it's going to be more than 0. The spread would be 0 if all the values were 2, which they're not. So what we could do is find the absolute distances from the mean, where we take each one of those distances as positive. So for example, in the previous example, that'd be distances of 1, 1, 0 and 2. But like I've said, this is really unwieldy. Unwieldy just means really clumsy and awkward, and it'd be really problematic for most calculators. There'd be lots of fiddling around to do one number take away the other, or to switch the order. So to get them all as being positive in a quick way is really awkward indeed. So is there another way of ensuring we get positive, meaningful values, rather than switching the order and making it awkward on ourselves? Well, yes, there is. So what could we do to the values to ensure that they always end up being positive and meaningful? So again, just return to this graph of the data points relative to the mean 2. Again, just to recap, the distance from the mean, each point subtract the median. So what we had, this one here, 1 take 2 gave us minus 1. The other one, take away 2, gave us minus 1. 2 take 2 was 0, if you remember. And the last one, this 4 take 2 is 2. Now we added those together, we got a problem. Add them together gives us 0, which was meaningless, wasn't it? So how can we make it meaningful rather than meaningless? What can we do to any number in the world to transform it into positive in a way which you've seen before and are very familiar with? What we could do is we could square each deviation. So we could square each number, couldn't we? So minus 1, if we do minus 1 squared, minus 1 times minus 1 gives us 1. This minus 1, square it, that gives us 1 as well. 0 squared, not too hard to do this one. 0 multiplied by 0 is still 0. And lastly, 2 squared is 4. So now we've got something we can work with. So now, if we think about what we can do with this, we could sum all these together. So if we add up all these squares of the deviations, which is sigma of the difference squared, sum of the differences all squared, let's see what we'd get. So 1 plus 1 plus 0 plus 4, add these together, we get a total of 6. Now we've got that total, we can now find the mean value for the squares of the deviations. So the mean of the squared deviation would be the sum of what we just worked out, which is 6, divided by 4, and 6 divided by 4 is 1.5. So we're making some progress here. The trouble is, we're not so much interested in the squares of the deviations. We want to work out the mean of the deviations themselves. So we've squared them, but we want to work out what the mean of the deviations is on their own. So we need to sort of undo the squaring process. We squared them to get them positive. Great, that solved that problem. But by squaring them, we've inflated them. So how can we undo the squaring? To undo squaring something, we can then square root it after. And this is called standardizing. These are the standardized deviations. This is, in essence, what the standard deviation is. So therefore, the standard deviation is we sum together the squares of the deviations, we divide by n to get the mean of the squared deviation, and then we square root that to get the standard deviation instead of the standard mean, instead of the standard squared deviation. So that's how we do it. Now, if you square the standard deviation, and this does actually have some uses as well. So the square of the standard deviation is called the variance. The other way around is you can think of the standard deviation as being the square root of the variance. So in our example, we had the sum of the squares as 6, and there are 4 data points. And so we had this value here as 1.5. So for our example, the standard deviation was the square root of 1.5, and sigma squared is the square root of 1.5 squared, which is 1.5. So as a decimal, the square root of 1.5, let's give it to 3 significant figures. So square root of 1.5 is 1.22. So there's other ways these formulae can be changed into different forms. So both formulae for standard deviation and variance can be manipulated into different forms that are more calculator friendly. So it can be shown that the standard deviation is the sum of the squares divided by the number of values minus the mean squared. The variance can be seen as like this, just without the square root. So the sum of the squares divided by the number of values. So it's like the mean of the squares divided by the mean squared. So that's quite a nice ring to it. So like I've just said, this one here, you can think of it as the mean of the squares minus the square of the mean. So before we move on as well, I just want to show you how you can do this on a calculator. So I'm going to give you some worked examples in a second, but just now I'm going to show you how I can work this out on a calculator. So what we can do is press Menu, toggle down to 6 for statistics, press 1 for one variable calculation, then input the values here which you want to find the standard deviation of. So if you remember, I'll make the screen bigger so you can see what I'm typing in. If you remember in our example, our values were 1, press equals, 1, 2, and 4. Press equals, then press AC to clear the display. We now press Option, then we press 2 for one variable calculation, and we're looking for sigma. So the standard deviation for ours was 1.22, and the variance, sigma squared, was 1.5, which is what we did have doing it manually. So in these next examples, I'm going to show you how you can do this manually, but ultimately the end goal is to get yourself comfortable and efficient doing these and checking them with the ClassWiz. So without further ado, let's have a look at some worked examples. So worked example 1, calculating the standard deviation of a discrete data set. So calculate the standard deviation of the following data. And so let's use this form here. Okay, so doing it manually. So these values here are just x. These are the variables. Okay, so what we can work out here is the mean. The mean is x bar, so we add them all together and divide by how many. So there's 1, 2, 3, 4, 5 values. So we're going to do 4 plus 5 plus 6 plus 7 plus 8. Divide that by 5. And what you should see is that the mean is 6. There's also symmetry as well. The numbers are going up evenly, uniformly in ones, and the middle number's 6. So the mode will be, so the median will also be the mean. So x bar is 6. We also need to do x squared for each one. So 4 squared, 16, 5 squared, 25. Just some square number revision, really. And 64. Now we've got all the x squares. We can sum these. So the sum of all these x squareds, I'm going to cheat here, just going to use a calculator. Get into the proper mode again. So mode 1. So 16 plus 25 plus 36 plus 49 plus 64 gives us 190. So we can now use this formula for the standard deviation. So the standard deviation is going to be the square root of 190 divided by the 5 values minus the mean squared, so minus off 6 squared. So let's try this. So we're going to do the square root of 190 over 5 minus 6 squared. We get root 2 exactly, so SROD 1.41. So that's the standard deviation. I'm now going to show you the calculator method for doing this. So get the calculator, menu, go to option 6, one variable, so type in 1 for one variable calculation, and type in the values one by one. So 4 equals 5 equals 6 equals 7 equals and 8 equals. Once you put all the data points in, press AC, then OPTN, then click on one variable calculation. So number 2, then we're after where it says sigma x. So where it says sigma x, just making the screen bigger for you, sigma x is 1.41 to 3 sig figs, which is exactly what we had here ourselves. Put the calculator back to normal mode. Now we'll have a look at the second worked example. So worked example 2. We're going to calculate this time the variance of this data set. So first of all, I'm going to do it manually. So these are our data points, x. We may as well work out the mean first of all. So the mean, we add them all together. 7 plus 8 plus 11, 13, 15 plus 22. And we divide that by how many data points we just added together. So 1, 2, 3, 4, 5, 6. So again, divide this by 6. And let's see what we get. So 7 plus 8 plus 11 plus 13 plus 15 plus 22, all divided by 6. That gives us, it's decimal, so let's leave it now in exact form. Let's leave it as just 38 over 3. We can round off after. Now we need to work out these values squared. 7 squared, 49, 8 squared is 64, 11 squared, 121, 13 squared is 169, 15 squared is 225, and 22 squared, I don't want to re-record this by making a silly mistake, so I'm not going to trust myself too much. 22 squared, just to make sure I don't fluff it, 484. We now add together these to get sigma x squared. So if we add together all these values here, so 49 plus 64 plus 121 plus 169 plus 225, whoops, put an extra 2 there, that was careless, plus 484. We get 1112. So therefore the variance, sigma squared, is going to be the sum of the squares, so 1112 divide by 6, subtract the square of the mean, so subtract 38 over 3 squared. So let's calculate this. Let's move to the side. So 1112 divided by 6 minus 38 over 3 squared. We get 224 over 9, which to 3 sig figs is 24.9. And that's the variance for this data. I'm now going to show you how you can work this out using the class whiz, which is much more powerful. So we get these data points here. Go to the side actually, so I'm not hiding any data points. So we press menu, option 6, one variable calculation, and type in the values. So we have 7 equals 8, press equals 11. So after each one, you just press equals to enter it. 13, 15, 22, press equals, then AC to clear. Then OPTN, press 2 for one variable calculation, and to make the screen bigger so you can see what it says, you can see here that sigma squared x is 24.8 recurring, which, like we said, to 3 significant figures is 24.9, which is what we got manually. So get used to this class whiz and get used to it soon. It is an absolute lifesaver. Finally, before you attempt the exercise on your own, I've got a couple of questions for you here in this student task. So A and B, two different parts, calculate the variance and standard deviation for the following data and give your answers to 3 significant figures afterwards. So 2 things you could do. First option, do it manually with using these formulae here for standard deviation and variance. And the second option, which I definitely want you to do, either on its own or second to manually, is to use your class whiz to work these out. Using your class whiz to do standard deviation and variance is an absolute must-know. So, doing them those ways, pause the video now, try part A and try part B, and then press play when you want to check your answers against mine. Okay, so here are the answers. So here's the answers for the first one. Variance 9.33 and standard deviation 3.06. This image here is what you should have seen on your class whiz screen. And for part B, standard deviation is 2.27 with the variance as 5.15. And again, this is the image you should have seen on your class whiz display, and I've underlined which bits you're looking out for to find standard deviation and variance. So standard deviation is blue, sigma x, and variance is sigma squared. So now it's over to you lot to try some questions on your own. So if you could try these questions, just 1, 2 and 3 from exercise 2D in the Stats and Mechanics book for year 1. Let me know if you're getting stuck. Check the answers in the back of the book, or if you can't access me that way, do drop me an email or leave me a comment in the comments section of this video. Thanks for listening, do consider subscribing if you can, and I'll see you in class or around hopefully very soon. Thanks again, and bye for now.